Hi, you guys. This is section 7.3 integration by parts. So, as always, make sure that you guys have your heading and go ahead and copy down the FLT right here. Play whenever you're ready, okay? Okay, so first off, good job at signing up for BC. It's not an easy course. You guys are continuing off from AB. I want you guys to keep in mind that no matter how you did on the AP exam, you have sort of a second chance at passing both the BC and the AB exam. And I'll talk about that later on as well, okay? So for today, BC, we start off by continuing off on where we learned with integrals, okay? So back in AB, you guys learned how to integrate simple functions. And then when it got a little complex, you learned how to use something called U substitution. So there are actually a couple of other ways or other methods that you need to understand. And before you leave this video today, make sure you know how and when to use certain things, okay? Whether it's U substitution or integration by parts, okay? So first off, let's review, okay? So remember how when you had an integral, you're hoping that the integral is something simple, for instance, x cubed dx, okay? When it's something simple like this, you definitely want to just think about all of your rules. In this case, this is the power rule, so we're going to raise the power 1 over the same power, and since this is an indefinite integral, we leave a plus c. Hopefully that's a good refresher for you guys. Here's another one. Let's say we're integrating cosine x dx, okay? Make sure that you guys have your calculus out or your set of formulas. But again, always try to pull away because we don't know what the format of the AP exam is going to look like this year, whether it's going to be in person or online. So at the very least, we want to prepare for the case that it will be in person, okay? So integral of cosine, the antiderivative of cosine is just sine x. Don't forget your plus c. So all of these basic integrals are simple because you could just jump straight to the antiderivative. But then you guys learned something called U substitution. So I just want to remind you guys, first off, in general, you use U substitution usually when there is a function within a function. Not all cases, and I'll show you some of the special cases afterwards. But for instance, if you had something like the sine of 14x dx, okay? So notice how you have a function inside of another function here. And most of the time, it will be a simple linear. But let's just keep this in mind here, okay? So what you do is, the long way is you let u be your inside function. You find your du, which is 14 dx, because the derivative of 14x is just 14. And since we only have a dx in our integral, we're going to isolate that 14 over to the other side. So this right here is the same thing as sine of u 1 over 14 du. And then you would just integrate it, and you would get 1 over 14. The integral of sine is negative cosine. And then you replace u back in with what it equals to, plus c. So that's really the long way. When you guys are in BC, I expect everyone to just approach the shortcut here, okay? And we'll do as many as we need to. So this is where I need your feedback, okay? So while you're watching this video, if you feel like you're not getting it, definitely please text me through Remind, okay? So usually when it's a linear, what you have to do is you just have to take the derivative, and then you take the reciprocal, Okay, we talked about this last year, but let's just refresh, okay? So in your mind, the derivative of 14x is just 14. The reciprocal of 14 is just 1 over 14. This is the guy that's going to go on the outside. 1 over 14. And then you think, okay, well, what's the integral of sine, right? So the integral of sine is just going to be negative cosine. And we keep the same angle. That's the faster way, okay? So let's try this out real quick. Suppose I gave you guys the integral of, oh gosh, e to the 30x dx, okay? So again, how do you know when to use U substitution, right? You notice that there is a function inside of another function. So in your mind right now, what you're doing is you're taking the derivative of everything in orange, and then you're taking the reciprocal of that answer. So play when you're ready, but go ahead and pause if you need time to guess it out. Okay, so what goes on the outside will just be 1 over 30, and the integral of e is just itself, so that stays the same. You guys should be able to do that with enough practice there, okay? Let's do another one. The integral of secant squared 1/3 x dx. Okay? Now you might have to look back at your calculus, but go ahead and do so if you need to. I'm going to ask you guys to pause here and then play when you have an answer, okay? Okay, so we know that the integral of secant squared of something is going to be some type of tangent. So I know it's going to be the tangent of 1/3 x plus the c. But notice how there is a function within a function. So we take the derivative, which is 1/3, and the reciprocal of 1/3 is just going to be 3. So we know 3 is going to be in the front. Okay? Let's do one more. Here we go. This is going to be 1/5 x plus 3 to the 10th power dx. Okay? So again, you could tell that this is a U substitution problem because it's a composition. There's a function inside of another function, okay? So go ahead and play whenever you're ready, but go ahead and pause now. Okay, so we know something to the 10th power is going to be something to the 11th power over 11 plus the c. We know that the inside always stays the same. So the only thing in question here is what goes on the outside. So remember, everything in orange. The derivative is going to be 1/5, and the reciprocal is going to be 5, so you have a 5 out here. Okay? So that's it in a nutshell for U substitution. So big takeaway, you guys. U substitution, how do you know when to use it, right? So usually, and I'll say usually because not always, usually when there's a function in a function, aka composition if you want to get fancy, okay? Now, there are some cases where it is U substitution and there's not a function in a function. And the most popular one, I won't show you all of them, is this here, the integral of sine x cosine x dx, okay? Now, if you can tell, this is not a function in a function. It's actually a product, okay, which makes it a little bit confusing, but it's one of those rare cases, okay? Now, think about this one here. We want to let U be something so that du is a perfect fit, okay? And with time, you guys are going to get good at this, okay? You may see it already, but don't worry if you don't. If I let U be sine x, if I take the derivative of U, I will get cosine x dx, which if you notice is a perfect fit right there. We have everything covered. So the integral of sine x, I'll replace it with u, and the integral of cosine x dx, I'll replace it with the du. So it makes it a lot easier, right? So the integral of u is just u squared over 2 plus the c. And then you replace your u back in there. Sine x squared over 2 plus the c. That's probably the most popular form. You may see other ones, but I'm not too worried about it, okay? Now, what happens if you can't use U substitution, right? So here's your list when you're integrating. And this is where you guys really have to practice, okay? You're hoping for something simple, right? So the integral of x squared or the integral of cosine x, something that doesn't require any manipulation, okay? Now that doesn't work. Your first stop is U substitution. And remember, U substitution usually is when you have a function and a function. Usually, okay? Now that doesn't work. This is where we jump to number 3 and 4, okay? We're only going to cover 3 for today, but this is called integration by parts. Okay, often called IBP. So, here you go. Usually, you use integration by parts when you see a product. Usually, okay? Not always, so keep that in mind. So, here's the quick proof of it. Okay? We'll come back to number 4 whenever we're ready, but there is a 4th part to it. So, remember the product rule. Okay? So U substitution was the reverse chain rule, okay? The chain rule is when you had a composition or a function within a function. So it kind of makes sense that U substitution is when you have a function and a function as well. The product rule, if you guys remember, is when you're taking the derivative of something times something else, okay? So that's going to be the first times the derivative of the second plus the second times derivative of the first. Okay, I use differentials here, but it's the same thing. Now, if we manipulate this a little bit, this is just how they got the formula, okay? If I wanted to get rid of this little integration symbol here, the inverse of a derivative is an integral. And what I do to one side, I'm going to go ahead and do it to the other. Okay, what ends up happening on the left side here is that integral and that derivative will cancel out, if you will, and then you're just left with uv. The right side here is going to be u dv. Actually, let me get rid of that dot there because it's implied, plus the integral of v du. Okay, so what I'm going to do here is just maneuver this over. I'm going to go ahead and subtract integral of v du on both sides. Now, why do we do this? I'm going to share with you in a second, okay? All right, so the integral of u dv is the same thing as uv minus the integral of v du. What the heck does that all mean, right? So here we go. I'm just going to reverse this a little bit. The integral of u dv, that's my right side, I just put on the left, is going to be uv minus the integral of v du. This is your integration by parts. Okay, make sure you guys are writing this down. Okay, so why is this helpful, right? So I want you guys to think about this. Why was U substitution helpful? Right, let's go back to U substitution. U substitution was helpful because after you substitute, you're hoping to make your integral easier. That's the hope, right? You're hoping to make your integral easier, or integrable, if that's a word. Okay, so same process with integration by parts. So if you look here, you're making an integral look like another expression with another integral. So what's the point, right? You're hoping that this integral looks easier. That's the whole point. Okay, it's the same process behind U substitution, okay? Now here, U and dv are going to be a product, and that's what you're looking for. So whenever you're seeing the integral of a product, you're usually thinking about integration by parts. So I'm answering the when for you guys, okay? We'll focus on the how in a second. So usually when you guys see a product, you want to think of integration by parts, okay? Now, how do you do that? I'll show you in the first example, okay? Here we go. Let me skip on to example 1, okay? Go ahead and write this down. Play when you're ready, okay? So here we have the integral of x cosine x dx. I'll write it again. Integral of x cosine x dx. I go down my list, you guys, okay? Definitely it's not simple because there's a product involved. It's definitely not U substitution because usually there's a function in a function, okay? So notice how this is definitely most likely integration by parts because there's a product, okay? So here's the thing. What you guys have to do, okay, is we need to declare what U is and we need to declare what dv is, which is probably the biggest task for you guys, okay? So the integration by parts, let me copy and paste that for you guys real quick. Let me erase this. Okay. I'll just leave this on the side here. Okay, so if we can make x cosine x dx look like a u dv, then we can see that it's equivalent to this statement over here. Okay, we're just trying to rewrite it in hopes that the integral is easier. Now this is where it gets challenging, right? So what is u and what is dv, right? So you guys have a couple of options here. I could let u be x and then cosine x dx be dv. I could let u be cosine x and then I could let dv be x dx. Okay. I could let u be x cosine x and dv be dx. There are a lot of combinations here. So right now, we're just going to guess and check. Okay? So let's see. What are we going to do? Let's say I let u be cosine x and dv be x dx. Notice how I'm using everything on here, okay? Okay, so if u is cosine x, then du has to be negative sine x dx. Okay? If dv, if the derivative is x, and this is where you guys gotta just think about it. If the derivative was x, what was v? Right? So what you guys are doing here is you're mentally integrating, or you're finding the antiderivative. The integral of x is just x squared over 2. And we won't put the plus c there yet. Okay? So here's what we have. You now have all the components you need to fill in this red box right here. So take a look. Right here we have uv. So u is cosine x. V is going to be x squared over 2. That's uv. uv minus the integral of v, and du is going to be negative sine x dx. Okay, so again, this is v du. I want you guys to take a look at this integral here. Okay, so remember, we're using integration by parts to make it look easier. Did we do that? did I make the integral look easier? I hope you guys are saying no. Actually, it looks a little bit more complicated, right? So this probably tells us that maybe what we declared as u and dv is maybe not a good idea here, okay? So I'm going to scrap this. I'm going to erase it, but you guys shouldn't erase it from your notes. You could just exit out, and you can probably just make a note that it's not a good idea. Okay, didn't make it easy. So let's try this. What if I let u equal x? Then that means dv would be cosine x dx. Okay, so if u is x, then du is just 1 dx, the derivative. Okay, if the derivative is cosine x, then v, the original function, is what, right? Play whenever you're ready. It's hard when I can't hear your responses, so I have to ask you guys to pause and play, okay? So if the derivative comes out to cosine x, then the original function v should be sine x, okay? So let's try this out now. So integration by parts, we're going to have, again, uv minus the integral of v du. So u v minus the integral of v du. And I'll write it up here in red so you can see uv minus integral of v du. Okay? So did we do what we were hoping to do, right? Did we make our integral look easier? Okay? Take a look at this integral right here. Does that look easier? Definitely, right? Because we actually turned this integral into something simple. So we keep going. So this is going to be x sine x minus the integral of sine x is just negative cosine x. And then I put my plus c there, okay? Now remember, we put plus c because it's an indefinite integral. So let me just clean this up here. Our final answer is going to be x sine x plus cosine x plus c. Okay? So we know the when, right? We noticed that x cosine x was a product, so most likely we use integration by parts. Now you might be asking, well, this is so complicated because how are you going to know what u and dv is, right? Because that takes up a lot of time, right? If only there was a way to figure it out every single time without guessing, right? There is a way. So here we go. I'll just, let me make some space here. So you guys should know while I'm erasing this, back when I was learning this, there wasn't a shortcut, a clean way. I actually had to guess and check every single time until I caught a pattern, okay? But some guy or girl out there came up with a shortcut, okay? So with integration by parts, so this is how you determine what u will be, okay? Obviously, if u is this thing, then dv is everything else, okay? So it's a phrase called liat or liat, whatever you want to call it, okay? This is actually representing all of the different functions, okay? So for instance, liat, L stands for logarithms, okay? I'll put logs. I stands for inverse trig, okay? A is for anything algebraic, T is for anything trigonometric, and E is for exponential. Okay, pause and play whenever you're ready, okay? So whenever you have a product, okay, you're going to have two different types, okay? It's going to be two different letters out of liat. So in this case, cosine x, okay, is something trigonometric, so that's a t, all right? X right here is just a polynomial. We call that algebraic, so that's an A. So out of A and T, so we're going from left to right here, you guys. Out of A and T, we're not looking at the alphabet, but we're looking at the phrase liats or liates. Which one appears first, the A or the T? Okay, A appears first before the T here, so we know that U will be X. And dV will be cosine X dx. So whatever appears first out of liates will be your U. Okay, let's put this into practice. Here we go. Here's example 2. Okay, so first off, is this a simple integral? No, it's not. Step 2, can I use U substitution here? Probably not, because there's no function in a function. Okay, should I look at integration by parts? Most likely, because there's a product here, you're multiplying one function with another function. So we'll probably use integration by parts. Okay, so let's take a look. X right here, out of liate, X is something algebraic. E to the X is something exponential. Okay, so I'll write it here again so I don't have to scroll back. Out of A and E, which one appears first in the phrase liate? Right? So A appears first if we're going from left to right here. So U should definitely be X. Okay? So it takes out all the guessing for you guys, which makes your problem solving a lot faster. Okay? So that means dV will be the rest, e to the x. Don't forget the dx, okay? So if u is x, then du is dx, because the derivative of x is just 1 dx, okay? If the derivative is e to the x, the integral of e to the x is just e to the x. Okay? So here we go. The integral, so if we're using integration by parts, remember it's going to be uv minus integral of v du. Some people like to remember the phrase ultraviolet voodoo. Ultraviolet voodoo, up to you. I just memorized the mathematical phrase, okay, but whatever helps. So here we go. So it'll be u v minus the integral of v du. Okay, so you're learning all these tricks, you guys, but don't forget, why are we using all these tricks, right? We're hoping to make the integral what? We're hoping to make the integral easier, right? Can I integrate e to the x now? That's a simple integration. So we did make it easier. So here we go. That's just going to be x e to the x minus the integral of e to the x is just e to the x. And don't forget your plus c because you're dealing with an indefinite integral, okay? Okay? So throughout this whole video, definitely text me if you guys have questions, okay? I'll be live making sure that I answer your questions there, okay? All right, so here's part C. Part C or example 2? I forget already. You know what? Let's call this example 3. You guys know me. I never remember my numbers. Example 3, okay? I'm going to actually let you guys do this on your own. So play whenever you're ready to look at the solution, okay? Okay, here we go. So here I definitely know that it's not simple. There's no function in a function. So most likely integration by parts because we have a product, okay? So x squared is something algebraic. Natural log is something logarithmic. And out of liate, out of L and A, L appears first. So U should be the natural log of x. And dV should be everything else, x squared dx. Okay? All right, so if I know u, then du is just going to be the derivative, which is 1 over x dx. If dv is x squared dx, then the integral is just x cubed over 3 plus the c, but we won't write that, okay? Okay, so integration by parts is ultraviolet voodoo. So u v minus the integral of v du. Okay, so let's pause and check here. Did we make our integral look easier? Now, if you're looking at it like this, you probably think that it's still complicated, but we actually did make it a lot easier here if you just clean it up. So that 1 over 3 can just pop out on the outside. That 1 and this 3 right here, we could just pull it out of the integral. And x cubed over x is really just x squared if you reduce it. Okay, so now look at your integral. Is the integral easier? It is. We actually make it look a lot more simple, right? So here we have natural log of x times x cubed over 3 minus 1/3 times the integral of x squared is x cubed over 3. Don't forget your plus c. You guys could definitely simplify this a little bit more, but seeing as how you guys are in my BC class, you know the idea of equal is equal, okay? So we'll try not to focus so much on the minor details of evaluating, okay? Hopefully you guys got as far as you could. Let's keep going, okay? So here, we'll call this example 4. Go ahead and write it down. It's already titled for you guys, repeated use of integration by parts. Sometimes you will have to run this trick multiple times, okay? So the first part to that, I'll do with you guys, okay? Again, it's not simple. There's no function in a function, so there's no U substitution. But there's definitely a product, so we'll try to lean towards integration by parts. So here I have what 2 letters, right? X squared is something algebraic. E to the x is something exponential. And out of A and E, A appears first, right? So we'll let u equal x squared, dv equal e to the x dx. Du will just be the derivative 2x dx. And if the derivative is e to the x, the integral is just e to the x. That's pretty easy. Okay, so ultraviolet voodoo, here we go. U v minus the integral of v du. Okay, did I make my integral look easier? Doesn't look any easier, right? But I did follow the right steps. A and E, the algebraic one was U. Okay, so here's a case where you will have to run it twice. Okay, first, before I do anything, I'm going to go ahead and take that coefficient 2 out of there, just to clean it up a little bit. Okay, so we're just going to look at everything in orange right now. Everything behind it, we'll kind of come back to it later. So if I'm looking at that, we're going to run it one more time, okay? Again, x is something algebraic, e to the x is something exponential, so u should be x, and dv should be e to the x dx, causing du to be dx, and v to be e to the x. And if you're not sure why you're not getting these values or how I got it, text me. I'll explain it further, okay? Okay, so just to make sure we didn't leave anything behind, everything that we were ignoring, I'm just going to bring it right over here, x squared e to the x minus 2. And then a lot was going on in here. We're going to replace that with round 2 of your integration by parts, okay? So this is going to be u v minus the integral of v du. Did we make our integral easier? So this actually took two different integration by parts to make our integral look easier. Okay, so we did do what we wanted to do. So here we go. We have x squared e to the x minus 2 times the quantity of x e to the x minus the integral of e to the x is just e to the x plus rc. Okay, and you can distribute that -2 if you guys want to. I'm just going to go ahead and leave that there because it's not really the big part of this problem there, okay? So this is a case where you have to run it twice, all right? So here's one for you guys to try. Okay, I'll call this part B. Go ahead. Okay, play whenever you're ready. Okay, I'm going to work it out right now. So here I have A, it's something trigonometric, so U is definitely going to be x squared. dv is going to be sine x dx. Notice how I'm going from u to dv. Try not to go from u to du and then dv to v, okay? Always go horizontally. So du will be 2x dx. V will be negative cosine x. Be very careful, you guys. So u v minus the integral of v du. Definitely not easier, but let me clean this up a bit. I'll have a positive 2 if I take out that negative and that 2 outside the integral. X cosine x dx. So if I run it twice, u here should be x because it's algebraic and it appears first before something trigonometric. dv will be cosine x dx. du will be dx. V will be sine x. Okay? Right up top. Okay, so we're going to have negative x squared cosine x plus 2. And then we're going to have x sine x uv minus the integral of v du. Okay, running out of space there. So although a little bit complex because we're writing a lot, we made the integral look easier. Okay, so negative x squared cosine x plus the 2 x sine x. The integral of sine is negative cosine, but with that additional negative on the outside, that causes it to become a plus cosine x. Don't forget your plus c. Okay? So hopefully you guys got it in the right direction there. Let me know if you didn't. I'll clarify if we need to, okay? Just real quick. Here's example. I think we're on 4. Let me double check. 5. Okay, how's this different, right? So hopefully you noticed that there are bounds here. We have a definite integral now, right? So not a lot has changed. Maybe just the way that you write it changes a little bit, but here we go. Do we use integration by parts? Probably. We have a product here. We have something algebraic, x, and we have something trigonometric. Right? So u should be x, dv should be cosine pi x dx. Okay. So du should be dx. And I'm going to have you guys pause here and play when you're ready, okay? Really think about what the integral of cosine pi x is. We talked about it at the beginning of today's lesson. Play when you're ready, okay? This right here is a mental U substitution here. You have a function in a function. So what you do is you integrate cosine, which is just sine of pi x, but notice how I left a space right there, right? That coefficient is going to be the derivative of pi x. So the derivative of pi x is just pi, and the reciprocal of pi is going to be 1 over pi. Make sure you guys understand that before we move on, okay? All right, here we go. So we have ultraviolet voodoo. So U V minus the integral of V du. Okay. Did we make our integral look easier? We actually did. Okay, even though it kind of doesn't look like we did. But that right there, you should be able to integrate. Not simply, but it may require U substitution. Okay, so let me first go ahead and scoot out that 1 over pi so it looks a little bit easier. You could always take out coefficients, okay? Okay, ooh, that was a gross dx. Okay, so here, this right here is U substitution. There's a function in a function, right? So again, there's a lot going on here. There's a lot of layered pieces, but you guys just have to just practice, okay? Here we go. So this is going to be x times 1 over pi sine pi x minus 1 over pi. And here's what I usually do. I stencil everything else out first so that I don't mess with the value of the problem, okay? All right, sine of pi x is U substitution because there's a function and a function. So the integral of sine I know is going to be negative cosine. Okay, but it's U substitution. So the derivative of pi x is going to be pi. The reciprocal of that is going to be 1 over pi. Okay, now I don't put a plus c here. So the only thing that changes, you guys, is right here. We have bounds. Okay, so what we're going to do is we're going to go back and we're going to put in our bounds. We're going to go back and we're going to put in our bounds. Over here, we're going to put in our bounds. But the only thing different is right here. We have to put bounds for that section as well. Okay? Okay, so that's the hard part. Now we just write it out and then we're all done. So here on the left, you just plug in, remember, you plug in your upper minus your lower. So here we go. Let me highlight this so you guys can see it. I'm going to take care of everything in green right here. In green. So upper will be 1/2 times 1 over pi sine of pi times 1/2. That's upper. Minus lower is going to be 0 times 1 over pi sine pi times 0. Okay? That's the green. Minus 1 over pi. Now in here, I'm going to have negative 1 over pi cosine of pi times 1/2 minus negative 1 over pi cosine of pi times 0. It looks gross, you guys, okay? Because there's a lot going on. But remember, they really don't care about this part. As long as you're plugging in upper minus lower, we could actually leave this problem as is. So you guys have an advantage because you already know the strategies to the AP exam. Okay, so although you have to write out a lot, you don't have to compute it. Okay. Okay, so here's the thing. So going back to this problem or this idea where you have to use your integration by parts twice, there's actually a fast way to do it. Okay. Now, let me first introduce you what it's called, okay? It's called tabular integration. This trick is fast, but 1, you have to be really organized, and 2, it doesn't always work. Okay? So, notice, you can only use tabular integration when you have of the following: x to the n which is something algebraic, and the following, something trigonometric like sine and cosine. It wouldn't work with any other trig function, okay? And something exponential. So if it's a and t, generally, or a and e, you could use tabular integration, okay? It is faster, but again, it doesn't always work. So I'll leave it up to you if you want to use it. The AP exam will recognize it if you're using tabular integration, but use it at your discretion here, okay? So take a look. Here's an example. I've lost count. I think this is 6. Okay. Play whenever you're ready, but go ahead and write that down. We can use ultraviolet voodoo, but this is actually going to take 2 rounds of it, okay? Some problems it takes a couple rounds, more than 2, okay? So I noticed that this is an A and an E. So right away, I know I can use a tabular method, which is integration by parts, just faster, okay? It looks a little weird at first, and it's really robotic. There's no logical sense to it. I'm sure there is, but I haven't looked at the proof yet, okay? So here's what you do. You leave a column for derivatives, and you leave a column for integration, okay? Your derivative will be your algebraic, always, okay? So in this case, it's x squared. Your integral will be e to the x. Here you don't put a dx, because in the end, it's going to solve itself, okay? This is where it gets new, okay? Nothing difficult. So your derivative column, what you want to do is you want to keep taking the derivative until you get down to 0. Okay, so here we go. The derivative of x squared is 2x. The derivative of 2x is 2. And the derivative of 2 is 0. Okay? That's how you know when to stop. All right? Now with your integrals, you want to keep going as far as how you went with your derivative. So we went down 4 lines. So e to the x, since e to the x is easy, integral of e to the x is e to the x. Integral of e to the x is e to the x. And integral of e to the x is e to the x. Okay? And this is where it's really a trick and not logical. I'm not a fan of tricks, but I mean, if it gets you your answer faster, go for it, right? You connect your diagonals. Okay? You never play with your 0. All right? When you connect your diagonals, you're multiplying it. Okay? But you start off alternating positive, negative, positive. Again, if you want to look at the proof, you'll probably make more sense of it. But that's not something that I would want to waste my time on. Okay? So here's what we do. We look at the first connection. We're multiplying x squared with e to the x, and it's positive. So positive x squared e to the x. Okay, now we look at our second pairing, and it's a minus 2x e to the x. Now I'm circling it for you guys to see. When we actually do this, we don't write out the circles, okay? And the last pairing is going to be 2 times e to the x, and it's going to be multiplied by a positive, so 2 e to the x. And don't forget your plus c. So this here is going to be x squared e to the x minus 2x e to the x plus 2e to the x plus c. You jump straight to the answer without actually having to do the integration twice. Okay? If you happen to like it, remember you could use it, but does it always work? No. So know your conditions, okay? Know when you can use it and know when you can't. Okay? Here's one for you guys to try. Let's call this part B. Okay. I'm going to have you guys do it. Play whenever you're ready to look at the answer. Okay. So right away, I know this is A, this is T. Definitely possible for tabular, even though it says tabular right here. So derivative, integral, x cubed, sine x. Remember, derivative will always be the algebraic one, okay? So derivative 3x squared, derivative 6x, derivative 6, derivative 0. Okay, integration, make sure you guys watch out for this here, okay? Integral of sine is negative cosine. Integral of negative cosine is negative sine. Okay, and integral of negative sine is cosine. And integral of cosine is sine. Okay? It's okay if you don't produce those answers as fast as I did. Even I had to kind of think about it because there's a negative and the extra negative that comes into play. So take your time with it. Replay that if you have to, okay? Okay, and we're going as far down as till we get to that 0, okay? So here we go. Diagonals meet up. These don't matter. Okay, we start off alternating positive, negative, positive, negative. Okay, so if we look at the first pairing, it's multiplied by a positive, but cosine is negative. So overall, we have negative x cubed cosine x. Our next one will be multiplied by a negative, but there's also a negative in the sign, so that'll turn that into a positive 3x squared sine x. Okay, the next one here will be multiplied by a positive, but everything is positive here, so that makes it easier. Plus 6x cosine x. And the last one is going to be negative 6 sine x. Don't forget your plus c. Okay. If you guys actually had to do integration by parts here, the ultraviolet voodoo way, it would take 3 rounds of integration by parts, which can be costly with time, okay? I don't think you have to worry about going that far with the AP exam, but just know that the tabular method is there for you to use when it's applicable, okay? Here's one more for you to try, but I'll leave that there. And you know what? I think I'll stop there, okay? So before we conclude, remember, you guys want to know when and how to use U substitution integration, okay? So remember, you look for something simple, then you resort to U sub, but when do you use U substitution? Usually when there's a function in a function or a composition, right? If that doesn't work, you're using integration by parts. Well, how do we know when to use integration by parts? Usually when you have a product. Okay, now how do we use integration by parts? We talked about it the whole way through. So hopefully you guys feel good about this. Definitely practice. Don't forget to submit your notes and practice on your homework right away so I can help you out, okay? But if you have any questions, let me know.